pleasure to introduce Christopher Tabor, research scientist at Air Force Research Lab. And Christopher is going to be talking about integrating liquid metals into e-textiles. And with no further ado, Christopher, the floor is all yours.
Thank you very much for the introduction. Yes, so my name is Chris Tabor. I work at the Air Force Research Lab in the U.S. And what I'll be talking about today is some work that we've done to accelerate and transition liquid metal-based materials into an ink solution so that it can be printed for stretchable electronics. And so with that, we'll go to the next slide. Maybe I can advance slides. Can I get a confirmation that that worked? All right. So as working at the Air Force Research Labs, I am in the Materials and Manufacturing Directorate. We look at new materials development that is high risk but high reward to be able to transition some of those technologies out into the commercial space. The Air Force labs, the DoD labs, do not make anything specifically. What we do is we do the engineering and the science ahead of time. We try to transition in from academics and some of the really cutting edge research and try to transition that across the valley of death into commercial entities so that they can now be used for dual use, but specifically military use case scenarios. And so there's a wide range of materials that we work in, from metals, ceramics, polymers, semiconductors, composites, biomaterials, and anything that touches those types of materials or the manufacturing of those materials is what we're very interested in. So the next slide, please. The one that is of, oh, I'm sorry, I am driving slides. The one that is of most use, or the one that is most dear to me, is this material that's a liquid metal at room temperature. And so many of you may be familiar with these types of liquid metals. I think there's a talk tomorrow from Professor Dickey looking at liquid metal-based electronics. And I'll just give a brief overview of what this system is. It's a gallium-indium alloy, and this is a eutectic blend that is a liquid at room temperature. But what makes it very unique, besides it being non-toxic, it behaves very much like mercury, except that it has a very thin skin that forms on the outside of it. So this thin oxide skin that forms nearly spontaneously with any oxidizing media, and that's water or air, will help mechanically stabilize the fluid. And so this mechanical stabilization does not happen in nearly any other fluid that exists. And so it's a very unique, very interesting scientific system. What we've done here just to demonstrate that is we've spread the liquid metal across, just kind of blade coated bulk liquid metal, gallium indium alloy across a sheet, and then removed the oxide in specific locations, just where the lettering is at. And you can see the high surface tension of the metal has actually drawn that material away from those areas where the oxide's removed. And so what this got us thinking about is if you can control and understand this oxide system, this outside oxide shell, you now have a tool set to be able to really control and engineer this incredibly fluid conductive system to do a lot of different application spaces. Unfortunately, so a lot of my slides have some very nice videos in them, but unfortunately, we had to switch to a backup here because I wasn't able to cast. But these, so these should, a lot of these should be videos, and I'll have to describe quickly kind of what you'd be seeing. You can extrude out this fluid. There's a lot of ways that you can extrude this out from a head. You can do pressure or pneumatic displacement out of these pressure heads to be able to print down onto a surface. It works on most surfaces, and there's been companies that have pioneered this to try to demonstrate that you can print down liquid metals from an extrusion-based platform, a variety of different types of liquid metals. One example is Liquid Wire, who has done a kind of a metallic gel material that can extrude out and provide some very interesting stretchable attributes to these conductive traces. What we saw, though, in the analysis of the area is we would like to be able to develop not just an extrudable material, but something that was akin to other printed electronics that you've seen throughout the presentations this morning, where you can take an ink and just place it into a traditional screen printing or inkjet printing system and have a printable liquid metal ink that's a colloidal suspension. And so that got us to think about